Okay, so I'm going to be going guys over the service. We talked before that the service in any building, Adam, every time you have any building, and we as electrical engineer, electrical designers, when we walk into this building, we first start with the service equipment. That's our single most important thing. That's the main panel. You guys have designed it for me. You put it in um, you put it in the building, the commercial building. You put it in the residential building, and you will do it in the industrial building in the spring too. So that's what this topic is. A couple of things about the service equipment. The service equipment, guys, always start with bringing the power from the utility using a transformer. So we'll talk a little bit about the transformers. Basic connection of the transformers. Granted, you guys are not electricians, and most of you, unless you decide to, will not be electricians. So, but we will talk about connections for these transformers, just in case if you become a project manager, Brian, and people are talking about connection, you don't look like you don't know nothing, right? At least know a few things about connection. They might not give you the tool to torque them, but at least know how they're connected. Different type of services. We'll talk about different type of services coming to the building. Various components of the service, as in the disconnect and grounding and bonding and what's not. We'll talk about equipment, service equipment, service disconnects, service overprotection devices. We'll talk about these one. And these are, Karen, is a fancy name for a big panel, the main panel in your building. That's really what it is, a big panel. The main panel you're building, it's called service equipment. It has to have a circuit breaker that acts as a disconnect and an overprotection device. You guys have sized it. Our panel was what, 500 amp. That's it. So it's nothing new. Installing service equipment correctly and connecting the metering compartment for the service equipment. For the project, Brian, that we had, you guys put the CT cabinet outdoor and you put the meter next to the CT cabinet, right? That's one way of doing it. You're going to see it now. There's a couple of other ways of doing it. We also have a ground fault requirement on the services on the feeders. We will touch again on the ground fault requirement. When do you need a ground fault requirement for the service and the feeders? And with every service and feeder add-on comes something called grounding system that you guys are very familiar with. You came from the electrician program. You have done a lot of grounding and bonding. Brian, we did it with the industrial project, grounding and bonding. So we're going to talk about grounding and bonding, which is not fancy, a fancy name for driving a ground rod and tying a ground wire to it and bonding your neutral right at the service. It's really with a couple and bonding everything metallic in the building. So that's what we're going to talk about. So transformers, guys, we use transformers in the building, in the construction industry, typically not to step up the voltage, to step down the voltage. To step down the voltage, we use transformers. So we take a voltage at a higher level, we step it down at the utilization level. So a very good example, typically the service comes to us like this, delta Y, 13.8 K here, volt, of course, and this is typically 480/120 volt, three-phase. All these are three-phase, of course, or 208, typically 208/120 volt. These are the typical services that you come to a commercial building. Again, three-phase commercial building. Karen, transformers are two types: dry and liquid filled. Liquid filled transformers and dry type transformers. What they do, guys, is transformers are made out of windings. You guys have finished apparatus with us. They make set of windings on the primary, another set of windings on the secondary. They are coupled magnetically together, but they need to be insulated from each other. Coils and primary, secondary coils from each other. So what they do, either they have papers and what's not to isolate them, and or they have some type of a liquid that they immerse both the primary and the secondary in them, and that liquid will act as an isolating. It isolates them from each other so they can't short, and it acts as a cooling. It cools them. It helps guys cool these equipment. So immerse it's non-toxic liquids. Of course, you don't want to have toxic liquids. High dielectric components, highly insulating. So it acts as a cooling mechanism as well as an isolating mechanism for the coils. And that's why if you have an oil-filled brine at Excel, you can load that one. You can force it. Really, it's cool. It has good cooling on it. Okay. So the liquid, what does it do for essentially insulate? This is the key point, guys. Insulate the high voltage winding from the low voltage and help in the cooling of the transformer. A lot of people, guys, specify for smaller buildings, specify dry type transformer. They are cheaper, lighter. So we have dry type transformer. They're lighter in weight. Dry type, there is no liquid inside them, so you don't have to have liquid containment and what's not. And if you have liquid, and if it's flammable liquid, you have to put them in a vault or outside. You can't put them inside the building. So there has a whole lot of regulations that are related to if you have a liquid-filled transformer, putting it inside your building. Most of the transformers that we put inside our buildings, guys, are dry type transformer because of fire hazard. And because they're light and they perform as good as liquid type for the rating for a smaller rating. So transformers, core and coils are, so what do? The cores and the coils are open. So what they do is they design them in a way where they're open to a circulating of air. So the air will circulate and cool them. The single most important thing, Karen, about transformer is being able to cool them. These beasts are being cooked by a lot of energy and they generate heat. And that heat, if you do not dissipate that heat, it will kill that transformer. So the whole idea becomes, how do you design them if they're dry type to dissipate the heat? And you can see that they have a lot of vents on them and what's not. They design them in a way where there's a lot of exposure to the external if they are air cooled. And sometimes, Brian, I don't know if you went to the substation where they have big fans on them. Have you seen that fan-cooled transformers? Oil fan-cooled transformers. They have oil and they have big fans blowing at them. Have you ever seen these? Maybe we should we should organize a trip for Excel, man. That would be really cool. Can you work on that one? So we can walk into this substation. They have big, huge fans, guys, and blowing air right into the transformer to cool it. I can't emphasize, guys, the important thing for a transformer to work properly is keep it cooled. You don't want to confine it. So most of the transformers that we use, guys, in the electrical construction industry, most of them are dry type transformers. Most of them. Utilities use oil filled transformers. They perform better. They live longer. They can be abused more. Okay, so with the transformer comes something called unit substation. Unit substation, guys, instead of having the transformer sitting outside, Karen, what the utility asks you is you as an owner, like say Mayo Clinic Hospital, that's typical application, sport arenas, or 3M, you bring your 18,800 volt into this high voltage section. Look at the voltage. You disconnect and fuse it, then they are bussed internally into a transformer. This is all one big box. And Adam, we will be touring places where they have this in the spring. So they're bussed together internally. And here's your transformer, and it's bussed internally into another panel. So that's typically, this application, typically they use it in hospitals, sport arenas, nice cut, all in one. Okay. So you have your transformers, you have your 13.8 K, you have your transformers 1.5 mega volt amp, and you have your voltage, which is 480 slash excuse me, slash 48277 or 28120, all bussed together. Expensive. This is an expensive deal. And then the utilities can do their metering inside on the high voltage side or the low voltage side. Any comments, guys? Any questions about so-called unit substation? We will be talking a little bit more about unit substation in industrial project, guys, because it's more related to the kind of industrial a little bit. Okay, transformers, guys. When you have transformers, the article that talks about transformers, Article 450, the single most important thing about transformers is being able to protect them from short circuit using fuses and circuit breakers. They have two tables that can be used and soon to change. One table, guys, covers over 600 volt. The first one, if either the primary, Brian, or the secondary are over 600 volt, you use this table. The second table here, 450.3b, if the primary and, I can't emphasize the word and enough, and the secondary are 600 volt or less. So if you have a 480 transformer, 208/120, so 480 primary, 208/120, you're going to be using the B, the 450.3b. So Adam, the overcome protection device that they use with the transformers is meant to protect the transformers, not the supplying conductors, not the conductors. So that's why when we do transformers, guys, you have to pay attention that there are conductors to be protected, and you have to pay attention to the rule, the tab rules. I go through the tab rules, guys, for conductors in the industrial project. So when we put, when we have a transformer right here, and you put a fuse on this side, and a transformer, a fuse, and a disconnect on this side, of course. These fuses are meant to protect the transformer, not the conductors. They will be protecting the conductor when you arrange it based on the tab rules, which again, we will do them in the spring. Okay, so we have transformers used primarily to change the transmission high voltage. That's what we do in the building. Take the high voltage, transform it down to a utilizable voltages. There are a lot of connections, guys, that we went through some of them. The single most important one that we did in the residential project was the single phase. It can give you this voltage, 3-wire actually, 240/120, 240/120. That's the most important one. The center tab of this transformer is always the grounded one. And let me just show you as we talk about these guys. I'll show you a couple of pictures that goes with it here. So we talked about the substation here. Here's the transformer. Karen, the table that talks about the transformer. This is, you can see here's the primary overcome protection device, secondary overcome protection device, and 600 volt or less, over 600 volt. You can see this is primary and secondary protection. It talks about the impedance, not more than 6, I will give you guys example about the calculating of this Adam when we go to the spring, how to calculate overcome protection device for transformers, because we have it. But you can see it's divided into, here the author is dividing it into 5 sections here, right? 1, 2, 3, 4, 5 sections, depending on the primary or the secondary. I want to bring to your attention, guys, if you have a primary and secondary protection like this, you're going to have, for example, if the primary is over 600 volt, you're using 300% of a fuse, or a circuit breaker 600%. If the secondary over 600, still, here's your multiplier. If your secondary is less than 600, here's your multipliers. Okay? Again, Karen, we will go over this, the whole calculation for this, please, in the industrial, because that's when we have our transformer. So we'll dedicate more time in using this table on the industrial project. So for the time being, I can't emphasize how important this table is. It's also coming in the NEC code book directly. Here's how they do that. Here's an example, guys, how we size the transformer. Very quick example. You take the full load current of the transformer on the primary, you multiply by 1.25 because of the voltages. It looks like 600 in both, less than 600 both ends. And then you multiply by 1.25 and you go to the next standard overcome protection device. On the primary side, maximum size fuse on the primary. You size your conductors based on 1.25 and your overcome protection device based on 2.5. The secondary side, you size your conductors and your overcome protection device based on 1.25. Again, we will do this one, guys. We'll do the same example. Brian, you're not going to be with us, but the rest of you guys, when we have a 4,000 amp switch gear in the industrial project, you guys will have the exact example, and you need to size the conductor for it. Okay. So based on the table. So we'll do that one, guys, in details, Connection of transformers that we talked about, Adam. Here's how they connect the transformer. Single phase. That's how you get your single phase transformer. Look at the high voltage, low voltage. If it's you can also have 240 120 open delta. Open delta 240 120 center tap, they call it. Open delta 240 120 center tap. Can you guys see how the connection is? Again, the expectation, Karen, is not, you're going to be not an electrician, but if somebody says, say, the wiring for open delta, how do you wire an open delta? I would hope that that's how you connect them. You guys have done that. You should have done that in the second semester with us. Straightforward. When you make a delta, you series the coils and you bring a phase between every two coils, and you take the guts out of a transformer here, one of the guts X2 here, and you ground it. So these are different connection. If you have a delta delta, look at the delta delta, guys. Very easy. You know, when I teach it to the electricians, guys, how to wire, I always say to get a delta atom, all what you have to do is take all the coils and put them in series. Can you guys see that? Look at this. Here's one coil, two coil, three coils. Put them in series like this, all of them. And between every two coils, bring a phase. You got yourself a delta. That's as simple as this. The high voltage are always labeled H. The low voltage are always by manufacturer labeled X. That's it. High voltage H, low voltage X. No question asked. That's how they label them. Let's get you 480 or 600 1 voltages. The most common ones, guys, is this type of transformers. I mean, this type of connection where you take the primary delta and the secondary Y to get. Yes, go ahead, Adam.
So on that picture, the high voltage, show me where the three phases are going.
Where are they coming?
And so just those three. Okay, so
Phase A, phase B, phase C coming in, and phase A, phase B, phase C coming out. Make sense?
Yeah.
That's the high voltage. That will be the 13,800 kilovolt coming on this side. And this side will be 28120 or 480, whatever you want it to be. Good point. But so easy. I always tell the people because this is the exam prep, guys. So what they do is I said, here's a coil. Look at this. Aren't they all in series? And you bring them all the way back. See how they are in series? And then between every two coils, put a phase. Between every two coils, put a phase. Between every two coils, put a phase. That's a delta. What's the Y? Look how easy the Y is. The Y is bring one side of all the transformer tied together. All the transformers tied together, one side. Can you guys see that side? And that will be your neutral. And the other side of the coil, bring a phase A, phase B, phase C. Now how easy that is. So easy, guys, the connection. This is secondary wire is, yeah, obviously, I'm sorry, thank you. This is a 4-wire. Why? Thank you. Misprinted. Why don't you email the author? Yeah, it's misprint. It's I think it's carryover from the one before. So it's a Y. It's a Y. Any comments, guys, about this one? You wouldn't be able to get a delta like.
How could it be a 4-wire without making?
Oh, here's 1. Here's 2.
Oh, so it is 4-wire.
Here's 3. And here's 4.
But it's a Y, right?
It's a Y. Yeah. To get a 4-wire delta, you have to have center tap. The next one we'll see it. You'll see it in the next one here. Okay, so we have a center tab. I don't think, where did it go? Okay, I don't have it. Maybe not now the center tab. Center tab delta. Yep, the one before. So these are the connection I would like to show you guys. Here's open delta. We talked about the open delta. The open delta utilities use them. They have 2 transformers for the open delta. Adam and you guys wired them with us in the lab. We have 2 transformers to create a 3-phase system. 2 transformers to create a 3-phase system. The problem with them, Karen, is you have to derate them 86.6. So for example, if you have a 50 kVA, two transformers, 50 kVA, that will get you 100 kVA. You can only utilize 86.6 kVA out of it without burning it. Why? Because of lacking of a phase. So that's your open delta. Typically, we don't use it in the residential. The most common one, like I said, is your not four wire, four wire. The four wire delta that we guys, they take a delta like this, and here's one wire, two wire, three wire, and they take the guts of one of them, ground it, and they take a fourth wire. Here's your four wire delta. Typically in commercial, in certain, not commercial, in certain application where you have a small amount of single phase load and a huge amount of three phase load, guys. Well houses and what's not. Again, we will hit them on the industrial. Three wire delta, when you only have a delta like this, that can only feed your three phase loads. You don't have anything to feed single phase loads. The most important one that you guys live with in almost, I would say, 90% of the systems that you're going to be encountering is called four-wire Y, Adam. Three-phase four-wire Y. These are a Y like this, and here's all the phases, and here's the neutral coming out of here. And here's your phase A, phase B, neutral, we talked about it here, and we have C. In the US, here's the voltages that we use for it, 122.8 and 270. I don't know about this, but 277, 480. That's probably 90% of what the buildings that Michelle Cool Erickson will be working will be wired either this way, and actually out of 90, I would say 80% of them will be wired with this voltage because it's the most efficient voltage that we use in the US. The most efficient low voltage that we use. That's considered low voltage. What's high voltage? Higher than 600 volt. So please pay attention to that one. If anything, nothing else. So that's the most important. This is how we wire it. We looked at this diagram, guys, and we said this is not a delta. Thank you. This is a Y. That's the most common. Now, most of these are three transformer banked. They call them banked together, guys, to get you a single phase system. We did it in our lab. So if this was a 50 and this was a 50 and this was a 50, when you bank them together, this transformer is worth 150 kVA. Now, in the three-phase industry, the utilities, Brian works for them. They like to do this one because if one of these transformers crab on you, what happened? They rehook this system open delta and you're up and running, and then until they get another transformer, stick it in there. Cheaper. Now, though most of commercial buildings, bigger commercial buildings, they don't do it this way, guys. What they do is they have a big fat transformer, three-phase transformer equivalent to 150 kVA, sitting in the front or the backyard, feeding your building. Instead of two single transformer mounted on a pole, these are one big transformer sitting in the backyard typically.
What do you say about Excel?
Well, from an Excel point of view, because typically these are owned by utilities, this type of arrangement, and this actually as service. So see if they have a short if this is short and burn, only one will burn.
How would they go through? How would they do that?
Oh, we hook them? Very easy. Well, you take, here's one transformer, here's another transformer. You hook them up as open delta. One of them is gone now. From this side the same way, an open delta, and this will be grounded. So here's you got yourself an open. I'm sorry, this is not the grounded part. Here's phase A, phase B, phase C, and in this case, where's my neutral? This is a Y. You have to rehook them, and if it has a component right here, guys, that would be your they ground this, and that will get you your neutral. It's called open data. That's it. But typically they don't, so it only burn one coil instead of three coils. Yes, sir.
On the applications, can you explain a little bit about that, the difference in voltages when you do the center tap delta? Because that's also considered like a dial play.
This is what, if you're doing it this way, the wild leg would be between these two phases. It's okay. The wild leg between this phase, and the neutral, that'll get you the 208 in this case.
That's an open delta, isn't it?
The same thing.
Same thing.
There's center tab delta, give you wild leg, and open delta center tab will also give you center. Listen to the word. They say center tabbed. You know what a center tab is? I'm a transformer. You have two coils coming out of me, two wires. If you take one from my guts, you center tab me. That's it. So here's the transformer. Here's the X1 and X2 coming out of here. Up to this point, we did not send. We hook it up the way you want. If you take one from the gut of that transformer and ground it, you just center tab that transformer.
So on a center tab delta, what is the voltage on it? It's like a three-phase center tab delta. What happens?
The only reason why we center tabbed a delta is to get line to neutral 120 from three-phase system. The only reason.
So
208, 120, don't think about it. 480, 277, don't think about it. The only reason why we have a center tabbed open delta or closed delta is to get 240, 120 three-phase. The only reason. And how often do we do this in the building? Not a whole lot. That's why I said, guys, the Y, the 480, 277, is the most common way of doing it. 480, 277. Why? 90% of the time.
on that center tab delta, isn't there some kind of configuration that causes you? Don't they have to warn you that there's two phases that if you put them together, you end up with like 208?
Yes, they have a wild leg, phase B, typically the wild leg, labeled orange. And they have to warn you on the panel that says wild leg, high voltage to ground is 208. What questions though?
I think it appears in the chapter in the industrial. It's not straightforward.
And that's what we're going to be doing. Yeah. Yeah. Adam?
So that picture you drew right there, the 208, that line from C to neutral.
Yep.
So it hits C and B.
No, it's just a neutral. So just, so it should be, here's my neutral. It actually should be phase B if you connect them right. From phase, this one to the neutral, it's 208. If you bring a wire from the neutral and to phase B on a center tab delta, you get 208, you shall not use it. If you bring a wire from phase B to the neutral, 120. From phase C to the neutral, 120. From phase B to the neutral, 208. So, good ones, guys, good ones. Only on phase B. You still, then, Adam, you still have phase C and phase A to utilize. Yeah. Only 120 if you go phase to neutral, but if you go phase to phase, you get 240. Good ones. A lot of this stuff, guys, the open delta, if you can, I know, Brian, you've done that, but if you leave the open deltas for when we do the industrial, I talk a little bit about them more. Because typically in industrial application, they use them. So three-way of connection with the primary connected. Okay, so we're not going to talk about the method of bringing. Now, who decided what type of service comes to you guys is the electrical utilities. They will decide what type of transformer, 3 single-phase transformers or 1 big transformer. So be careful of that one. Most of the commercial building likes to have something called pad mounted transformer. You see this one in Adam and all Mishad Cooley prints when they do them, pad mounted transformer. A concrete pad in the backyard with a big fat green looking transformer typically sitting on it. That's what a pad, that's what the building that we designed has. They can be liquid insulated or they can be dry. As well as dry transformers. Typically dry transformers what we prefer. Fed by underground or overhead conductors, typically underground. The secondary normally enter the building through ducts or cables. So you have your transformer coming in here and you go this way to the building and this way to the electrical utilities on the pole. That's the most common application of the utility. We talked about the unit substation, guys, where they tie everything together. If you have unit substation where they have the transformer, the high voltage, low voltage, and a transformer all in one section. Um, so they can typically, if it's provided by utilities, you have to pay for it. There's some arrangement. Here's one way of connection, guys. Look at this one. We're bringing the power from overhead into underground. We came to the high voltage section. We transform it. We came back into my disconnect means. That's a typical commercial preferred pad mounted transformer. That's a lot of engineers prefer this way. Can you guys see that? We came from the top into sitting beautifully tamper resistant box sitting outside underground. Everything is hidden. Everything's underground down to the disconnect. That's the most preferred one. When you have pad mounted transformer, guys, they can have the CTs sitting somewhere here, and sometimes they have pad mounted transformer ammeter here. So the metering section that you did, Adam, we have a CT cabinet, we call it, CT cabinet metering section, either part of the transformer or another box sitting next to the transformer. Why do we have the CT cabinet, guys? In order to meter the power coming to us. In order to meter the power coming to us. So pad-mounted enclosures, or sometimes they put them in a vault underground. That happened, Brian and Karen, in downtown Minneapolis. They put them because do you want to put a pad-mounted transformer on Hennepin Avenue so people can mess around with it? So what they do is they put them in the vaults underground vaults. Utility pole or in the building. The metering guys, they can either put it on the pole or in the building or the CT cabinet where you put that metering for the utility type. They have two ways of metering so you can pay for it. One is called, guys, primary high voltage. The primary high voltage metering, so here's your transformer. What they do is they have a sensor here and they put the meter on the high voltage. That's the high voltage. The low voltage, they put the sensors here and they put the meter here. So Adam, if you put it on this side, it's high voltage metering. If you put it on this side, it's low voltage metering. So that's most of the metering will happen on the low voltage metering. The utility, the 480-277, not the 13.8. Very few customers, primary customers, have it on the high voltage. The electric metering, potential transformer, in order to do the metering, guys, there's something called current transformers and potential transformers that you need. Potential transformer, guys, take the 13.8 and convert it to 120. Current transformer takes 4,000 amp and convert it to 5 amps. And do you know why, Adam, they convert these? Now they put these into the meter. If you put 14,000 amp into a meter, what happened to your meter? Fried. If you put 13.8 into a meter, 13,800 volt in a meter, you fry it. So what they do is they have a transformer that converts the voltage into 120. Now they can sense the 120 and proportionally reflect what this voltage is. And also the same thing, the 4,000 amp, they have a CT transformer that converts it back to 5. So every time you see a 4,000 amp, if the system has a 4,000 amp, the meter only sees 5 amps. If we're pulling 2,000 amps, the meter will see 2.5 amps. Yes, Adam?
I thought you said that's a high voltage meter.
It can be on the high voltage or on the low voltage. Same. I'm just showing it on the high voltage side. It could be in the high voltage or the low voltage. The high voltage is where you put your CTs here. If you put it here, that's high voltage. If you put them here, it's low voltage. The meters themselves, Adam, they always work on low voltage. Otherwise, they'll burn them. Always. All meters work on low voltage. You know.
Why would they be metered at high voltage?
If you decided, if Dunwoody decided, the only time they do it if the customer wants 13,800 volt coming to their building to feed different equipment at that 13,800, That's what you meter. Typically, 5% of the people. You're talking about the UVM, 3M, major manufacturing, Gurdu. So that's the only time. Yeah. Very huge equipment, melting steel. Um, so that's the only time you have metering. So I want to refer you this one to the industrial, because in the industrial, guys, we talked about the higher voltages. Low voltage metering is what we do, guys. Let's focus on the low voltage. On the low voltage side, um, typically up to 200 amps, you can bring hot 1, 2, 3, and a neutral to the meter. 1, 2, 3 out of the meter. If it's 200 amp. If it's larger than 200 amp around, what they do is they have CTs. Here's what they do: CTs, current transformers, to a meter. The meter will be sitting here instead of the meter being here. So they don't bring the cables into the meter. They have a CTs if it's larger than 200 amp. So that's my my metering. Any comments, guys, about the metering? All what you need to know about the commercial project is if you go higher than 200 amps, which ours was 500 amp, you have to do CTs and pull these CTs into a meter. Pull these CTs into a meter. When you bring your service to the building, guys, I want to show you a couple of things here, a couple of pictures. Talks about the definition of. Here's a couple of examples of bringing your service to the building. So here's my transformer. We are bus ducting it all the way to the CT. Here's current transformers. The current transformers that convert it so I can measure it. That's one way, industrial. So if you hold your horses on that one, because that's typically for industrial. Here's a commercial building where you guys bring the power directly from the service all the way into the building. You have current transformers, high voltage switch here, and you have current transformers here to metering it. You have your transformer and you have your switch gear with the main into these. These are major manufacturers taking it this way. Take your power this way. Typically what we do, like the building that we did Adam, this is how we did the building, the commercial building that you're working on. Typically you bring the power into a transformer, out underground into, this is your main panel. That's typical application for the commercial building that we did. Yeah, this is just a transformer. It looks like they also have the CT cabinet in it and the meter. The meter either will be here or they take a conduit and they put the meter on the wall here. See what I mean? That's typical. Where they meter it. Here's another way of coming underground, under downtown Minneapolis now, where you work. They come underground, vaults into a meter here and into the building. So different application where they put their meters in. Different applications. Here's a typical meter, guys. The jaws that they have for the meters. If your voltage is 208, here's what you have: 208, 120. This is how it looks like: phase A, phase B, phase C. And if you're and the neutral, of course, with them. If your system is 208, 120 up to 200 amp, you have all the phases here plus the neutral, of course. So different configuration for different meters. That's what you have in your house. 120, 208. So when you buy a meter, 200 amp, 3-phase, that it will look something like this. If it's 200 amp, 120, 240, it will look something like this. How many jaws they have? They call these jaws, meaning how many phases you want to break. You know, so that's a typical application, guys, for your system in terms of the transformers. Okay, moving into when you bring, this is the most important thing. We did this one in the residential, if you guys remember. We said this called the service point. The utility is this is called service point, underground or overhead. That's your service point. The conductors, if you come from overhead, it's called overhead conductors, or underground service conductors, or service laterals, or service drop into the meter. From the meter into the first disconnect, this one, it's called service entrance conductors. From this one into the building, it's called feeders. So that's the terminology that the NDC guys code uses with it. There's service drop. These are the power conductors coming into the service point. My service point. From the service point into so you have your service For your service point into the building, that will be your service entrance conductors. Your service entrance conductors. Any comments, guys? Any questions? All what you have to worry about, Adam, is just service entrance conductors coming from the transformer inside your building. You have to size them. In our project, guys, the service point will be the CT cabinet. That's where we pull the conductors into the CT cabinet. Out of the CT cabinet into the transformer that will be owned and operated by the utilities. Owned and operated by the utilities. Okay, so that's a few of these, the service point and what's not. Okay, service, that's the service drop. The power lines are coming to your the power lines are coming to your building. Like I said, they're called service, let's go back into service drop right here. So my service drop, these are just a couple of terminology that they use, and again, we did them in the residential. The power coming to your building called service drop. Service entrance conductor, they take you from your service to the service drop, from the service drops into your equipment. That's called service entrance conductor. These are what we care about. We size these. Service entrance conductor, Adam, you size it. These are the cables for the 500 amp that you brought to me on your table. You call them service entrance conductor. Service drop, we have no control over. That's coming by the the electrical utilities. Service entrance conductor underground, that's what we also size if we're going underground. Service lateral, that's done by utility. That's coming from underground between the utility supply and the service point. Utility supply from the transformer to the service point. From the transformer to the service point. Service point, the point of connection between the facility of the service utility and the premises. This is the single most important thing probably, guys. Here's my transformer here. Here's my CT cabinet. I'm coming from here and from here to the CT cabinet, from here out into my building. So Adam, this cable here is service entrance conductor coming to my building, and this point here is called service point. Can you guys see that? This point is service point, which means from here to the building I own and operate, from here to the transformer, XFR, the utilities own and operate. Any comments, guys? Any questions about service point for the utilities? Typically, the CT transformer, Adam, for commercial building is your service point. Conductors, also service entrance. Now, the service entrance equipment, typically you have your conductors, your main switch or switches, metering compartment, all these are called service equipment. The service pad mounted three-phase, this is just for the building. So from the service, you guys typically pad mounted transformer sitting outside, and you're bringing the power underground with PVC conduit inside your building. So Brian, my friend, here's the building, the commercial project building. Can you guys see that we're paralleling three sets, bringing the cables here, and we're tapping these to feed different tenants. We're tapping these to feed different tenants. That's one way of bringing service conductors. You bring one service conductor, Adam, to the building, and from that service conductor you tap it. Can you guys see that? That's if you have multiple tenants in the building. That's how they typically do it. I will bring to attention, guys, the CT cabinet here and the meter. If it's higher than 200 amp, these are 200 amp. Higher than 200 amp, you have a CT cabinet here just to convert the amps into a lower amps where the meters can handle. Mistake number one, Adam, next time you put the disconnect after the meter, not before the meter. You don't disconnect the meter. Underground service conductors. So your underground service conductors, these are coming from the service point inside your building. Service conductor, terminate box, load calculation. The underground service conductor, you guys size and operate. So these conductors that these are underground service conductor. These, you guys will size and operate based on 220, Article 220. We size them and operate them based on Article 220. Service disconnects. Every service, guys, must end up with a disconnect and a fuse. They call this a service disconnect, and they call this a service overcome protection device. They're all sized based on the calculation that you do from Article 220. Article 220, you calculated loads based on Article 220. It has to be readily accessible and in or on the building, inside or outside, as close to entering the building as you can. Any comments, guys, about the disconnect? All this information, guys, you've done it. You've done it for the residential project and the commercial project as well, too. Service entrance conductors, these are what you guys size with me for your load calculation. You can, if you have a big, fat, fluffy boiler, they allow you guys to have a whole service for the boiler, just a service for the boiler, and you size it base 1.25 because it's a bigger load. Any comments, guys? Any questions? Let me summarize the service in two things. The service is made out of a transformer, guys, coming into a CT cabinet, from the CT cabinet into the service entrance equipment. Between the service entrance equipment and the CT cabinet, Adam, we call them underground service entrance conductors. The service entrance equipment, which is the main panel, must have a disconnect and a fuse or a circuit breaker. Okay, and it has to be accessible, located inside the building or outside the building. That's a different configuration of services you can get from the utilities based on three-phase or single-phase. Any comments, guys, before I'm going to give you a quick break and I'm going to hit the grounding. Again, grounding and bonding, guys, we'll talk about grounding and bonding in details in the industrial project, in details, from main bonding jumper to system bonding jumper, supply side bonding jumper, and what's not. But let's talk a little bit. I'm going to give you 7 minutes, and then let me just touch on the grounding and bonding, shall we? So, thank you. Let me just say a few things, guys, about grounding and bonding. I'm going to summarize grounding and bonding, Adam, as when you bring your service to your service conductors, you have to bond the neutral to the ground. So you take a wire and you go tie it to the water system inside your building. That's called grounding electrode system, if it's reliable. If it's not reliable, you drive 2 ground rods outside and you tie it to 2 ground rods. If you have a concrete encased electrodes, foundation with concrete array bars, you tie to them. And the whole idea, guys, with the grounding a system, the reason why we ground the system, Karen, is because of safety. If we don't care about killing people, we really don't have to ground the system. The reason why we have the grounding system is safety, pure safety. It will minimize the shock hazard, number one, and it will eliminate the fire, or will minimize the fire. So if you have, when Steve asked you guys to put that fixture, if the frame of that fixture happened to, the transformer is malfunction, and the hot is touching the frame, and the frame is not grounded, this is basically a trap waiting for you to touch it, right? So you go, Adam, on the ladder there, you touch that frame in one hand, and you're touching the some other grounded object. Now you act like a bulb, basically. You have 120 right across your heart. I'm not going to tell you what happened next. You joined the Lord so fast. So to minimize all this, guys, we send a conductor called equipment grounding conductor with all the branch circuits and feeders. And so that's grounding the equipment. Then we also ground the system. So the system that comes to the building is required to be grounded, most of the buildings. So we take one wire from that transformer and we tie it to the ground to reference ourselves to the ground for safety reasons. So that's probably the most important things. I'll talk in details about the sizing as when we go to the commercial industrial. Does grounding means connecting a conductor to the ground or extending the ground. There's a lot of definitions about grounding, guys. When you say grounding a system, you're intentionally connecting one wire to that system, to the ground. So the fault current travels in all directions. So that's why when we have your conduits, Adam, see if you have a ground fault right now in this conduit, the current will go through the equipment grounding conductor, if any, as well as through the conduit. So what does that mean to you and Steve and Karen when you guys torque all these lugs? Means the connector that you do have to be tight. Why do they tell you the connectors have to be tight, right? Because if when the current, if you have a ground fault, the current's going to go through the conduit. Now we're going to enter the box. When you enter the box, there's a connector there. If it's not tight, what's going to happen to that current? It's going to have an impedance. Impedance means going to arc, and it's going to create a fire. So that's why they tell you when you're doing electrical work, you have tight all these connectors, right? Wrench tight. Make sure they're wrench tight so they can carry the ground fault. So that's the whole idea, guys, of the ground fault. So ground fault current. So the code requires the ground fault path to be as smooth and as easy and as wide as possible. They allow you to use the EMT conduit, rigid, intermediate, the shell of these conduit as an equivalent ground conductor. Or if it's PVC conduits, you have to pull a conductor inside the conduit to ground all the metallic parts of any electrical equipment. Almost all the electrical equipment that made our metallic objects, from your refrigerator to the air handling unit to the chillers to what's not, have to be grounded. Why do we ground them? Because if accidentally that fixture is to, the frame of the fixture is to become energized, guess what's going to happen? We have a circuit breaker here, is going to see a ground fault, and it's immediately it will trip, indicating that, hey, do not go touch the object. It's a trap. So don't go there. So that's the reason, the main reason why we're using the ground. So bonding guys put things in the same potential. Adam, do you see the power pole coming down? Now what happened? What happened? This has to be bonded to the grid, and the grid has to be bonded to the equivalent ground conductor. Now what happened? It's carrying current, right? Now what happened? If this becomes energized, because of something malfunction in the whole grid here, it becomes energized. And Chad here, you hold one hand here, and one hand here. You got 0 here, 1 here. What's going to happen? The current goes right through your heart. It's a perfect shock. So that's why they bond all these power poles coming in. The ceiling grid that you're looking at, it's all bonded to the equivalent grounding conductor. So when you bond them, you eliminate any potential, any voltage between them and any accidental. It has to be accidental for this to happen. Any accidents to happen. What does that mean? Imagine this building has been here for what? We're almost 100 years, right? I'm sure it changed over them. So you saved lives for almost 100 years or 50 years. So it's not just today. You're thinking, when you design a building right now, think about 50 years from now, the people will be living with your design. Could it happen over 50 years? A lot of things could happen over 50 years, right? So a lot of people say, what's the likelihood that malfunction, right? Not nil over 1 year, 2 years, 3 years, 4 years. How about 50 years? So think of the depth of. Okay, so that's basically the bonding. Why we bond things, minimize the shock, guys, and facilitate the operation of overcome protection device. The NEC guys require any system 50 volts, over 50 volts, all the way 50 volts or over to 100 volts to be grounded, with very exceptions, very few exceptions. So so in the building that we have, you take a grounding electrode conductor and you tie it to one conductor in your system. That's called grounding electrode conductor. Grounding electrode conductor. So if you guys do me a favor, if you guys go to page 290, please, and I say please, 290, it will talk a little bit about the requirements of the grounding, 290. It talks a lot about a few definitions about the grounding, identified neutral and what's not. All these requirements in 10 foot and what's not. And again, I promise you, Adam, my friend, in detail, we're going to do about the grounding and bonding. All what I want you to know right now is you will take a grounding electrode conductor from the service all the way to the grounding electrode system, which happen to be the water or the concrete encased electrodes or a ground rod, and you tie that wire to it. That wire has to be continuous. It cannot be spliced, Karen. It has to be protected from physical damage. So that's basically what they're telling you. If it's connected to a rod directly, it doesn't have to be more than number 6. So that's what all these details that they're giving you guys about the grounding. But the system, sizing the grounding electrode conductor. So when we size the grounding electrode conductor, Karen, we use what we call it, we use this table, 250.66. You guys have sized the grounding electrode conductor for me in your load calculation. You take the service conductors coming to the building and you size it. Here's an example in the commercial project, guys. They're using 3 sets of 500 kcm conductors in parallel. When you add them, when you multiply 3 by 5, what do you get? You get 1500. Right? Here's a 1500. Then you take the 1500, gentlemen, you take it to table 250.66, which you guys have done it for me when we did the load calculation, and guess what you get? You get a conductor of 3/0 that you tie to your water system. Very simple, guys. A grounding electrode conductor, you take your conductors that you size with me, guys, for the service conductors, right? And go to 250.66 and find how many conductors you need. If you paralleled like we did, then all what you have to do is multiply that set by how many sets you paralleled, the size of one set by how many sets you paralleled, and go to the same table. There's something called, guys, ground fault protection. The ground fault protection atom is required on any system, 1000 amp, 1000 amp. So if you don't have 1000 amp, you don't even worry about it. And if the voltage is 480/277, 480/277. Guys, when the voltage is very high, Brian, my friend, and Karen, when the voltage is very high, and the current is very high, there will be ground faults high enough. There will be ground faults high enough that the ground faults are high enough that they can burn your building, but low enough that the circuit breakers cannot see it and trip. Because of this, Karen, my friend, the code requires you on the service as well as on feeders to put a specially designed device called ground fault protection. Did you guys hear me? So when you go, Brian or Karen, work for Michelle or somebody else, you're going to see the word ground fault protection. And that ground fault protection will get you, protection from ground faults that's high enough to damage your equipment, but low enough to not to be detected by the circuit breakers. Karen, any comments, any questions about the ground fault? Comments, questions? No? So that's what you're going to be doing. A couple of things, guys, the leftover of that one is just a couple of OSHA rules. You remember when you can't work on energized things. You cannot work on things energized based on OSHA, right? So that's just a few reminder that never work on equipment energized. You have to disconnect them and tag them and size them before you operate them. Only qualified people are required or allowed to work on equipment. You do have to warn the people from the arc blast hazard and turn the power off when you work on a piece of equipment. So that's what I wanted to show you guys. Let me see if I can have a couple of other pictures to share with you. We talked about these. Here's a typical wiring diagram, guys. You bring the neutral here. Adam, can you see these CTs right here? These CTs, they will take the current and convert them to a 5 amps and will be measured by that meter. You do them in anything higher than 200 amp. If it's 200 amp or less, here's how they do them. They bring the power right into the equipment. Look how they ground the neutral, the grounding electrode conductor, guys. Come right here on the service equipment and they ground it directly. Take it to the grounding electrode conductor based on the conductors coming into this conduit. This is the project that you guys are in the project in the book. Here's service entrance conductor coming in here, tab to feed multiple loads, size appropriately. And I know all of you guys have installed and sized this system. And if you don't know how to size it by now, after we did two, I think you should ask your friend Chad for a refund. You just wasted your time with us. Grounding and bonding, guys, very simple. Here's your equipment, grounded conductor coming in to the ground bar. You bond it to the enclosure based on the code. And then you take a grounding electrode conductor into the ground rod, which happened to be a water or a ground rod or grounding electrode system. Very, very simple. The utilities, Adam, from their side, they also ground and neutral. Can you get this is done by the utilities here. You in your building, you ground it right in here. You ground it right in here. This is the grounding and bonding, guys. So when you bring your grounding electrode conductor to the water pipe, you have to bond across the meter so the utilities can maintain their meter. You have to bond to the hot water. Can you see the hot water pipe have to be bonded? So all of the same potential, you bond to the concrete in case electrodes. Here's my neutral inside the switch gear. Here's my bar. You bond the neutral to the ground. You bond the conduit coming in. And again, I promise you guys, you will hear about grounding and bonding in the spring more than you can even imagine. I go through this in details with my sheets. This is bonding boxes together. So if this is non-metallic, metal raceways between metal boxes. If these metal raceways, the connectors here will bond you. If this is non-metallic raceways, you have to have an equipment bonding jumper between the two. System bonding jumper, Adam, we call it system bonding jumper, taking the neutral and bonding it to the enclosure of the service disconnect means or the transformer that you own and operate. In this case, if it's system, it's right at the transformer that you own and operate. The system bonding jumper. Bonding, the reason why we bond, we told you guys, because if this is to become energized one side and you touch both sides, that current can go right through your heart and it will send you to join the Lord so fast. Bonding the conduits, all the conduits, if they're rigid coming from underground, Adam, they have to be bonded. They call it, this is called supply side bonding jumper. I will spend more time on it when we go into the industrial because that's when we parallel. But it's sized exactly like the main bonding jumper. Same thing, guys. See all these conduits, they're coming here. If they're at the service, or if the service is 48277, and these are concentric and eccentric knockouts, you have to bond all these conduits. You see how they bond? Either daisy chain them like this, Karen, or you can take them one at a time. Either daisy chain them or take them one at a time. This is where we talk about eccentric or concentric knockouts. If the hole matches the conduit, I'm sure, Adam, you guys did it when you were doing it there. If the hole matches the conduit and the system is 48277, you do nothing unless that's at the service. Otherwise, you have to bond the conduit. You have to have a bonding bushing and bond the conduits. You guys, I know you're not an electrician. We emphasize this a lot for the electricians, but when you become a project manager, it's really nice to know all this stuff too. Okay, when you're doing bonding, non-conductive paint have to be removed so you can have good connections. If you have a flexible like this, Brian, my friend, and Aram, you have a flexible, you have to also bond around the flexible because flexible is not meant to as an equipment grounding or bonding conductor. The reason again why we bond is because accidents happen and energized conductors could get in direct contact with metal objects and become energized. The way they design the ground fault, guys, this is a ground fault. They have a sensor either around all the conductors or one sensor around each conductor. They sense the difference in the current coming in, coming out, and if it's substantial, it will trip the disconnect or the circuit breakers on a ground fault. Adam, this is only required for if your service is 1,000 amps. So if you've never seen it, never heard about it, I don't know if you guys talk too much about it in the construction, 1,000 amp or higher. And the voltage has to be 48277. If you use 240, 120, nah. If you use 280, 120, don't think about it. It's not required. So that's on a higher, that's what we do in the industrial project next time. So what happened, guys, if you can see, if you have a ground fault right now there will be current going right in here. So that CT will see the difference. Sense the difference, send the signal to this trip unit, and it will open the circuit breaker. It will open the circuit breakers. Different connections, different bonding of the water. You can see bonding it for safety. Different hardware that you can use. This is just the calculation that they did for their service, and they sized the service conductors. You guys have done that intensively with your friend Chad. This is 250.66, guys. So if my service conductors are 700, for example, then my grounding electrical conductor Adam is 2 aught, and my main bonding jumper is 2 aught. So if my service conductors is 3-aught, then my grounding conductor is number 4, and my system bonding jumper and main bonding jumper and supply side bonding jumper are number 4. Equipment grounding conductor, the 100 amp receptacle panel, if it wasn't EMT, if it wasn't fit with EMT and you need to pull a conductor, you have to pull a number 8 equipment grounding conductor with it. So there was a 125 lighting panel, or 200 amp panel. The 200 amp panel lighting, you need number 6 equipment ground conductor if it's not wired with an EMT conduit. Say if you put it with PVC. So that's so-called the equipment ground conductor. You do have to wear, here's Brian, a caution phase has a 208 volts to ground. That's that. If you have a high voltage section, you have to have this label right at the 480, I'm sorry, 240, 120 center tabbed delta to warn the people, hey, Mr. Apprentice, you shall not connect anything between phase B and the neutral because it's 208. And you put 208 across this is rated for 120, you have just burned it. And there's stories after stories of people guys burning equipment because they did not pay attention to that. So, okay, so that's basically all what I want to show you guys about this project. I can't emphasize, guys. I know you touched on some of this. You're designers, you're not electricians, like I said, but knowing all this, there's a lot of people, Adam, in the industry will be more than happy to use you as a drafter for the rest of your life. Now, how are you going to elevate yourself from a drafter into a designer and a project manager? The more you know about the electrical coding industry, the better designer and engineer you'll be. Really. I know it's a lot of stuff, but you're going to spend, if you're a young man, all of you guys and young people, you're going to spend the rest of your life hearing these terminology. It's not going to change a lot. You know what I mean? So the more over time, it will start sticking more and more. And I know it's a lot of information, though. Any comments, guys? Any questions? Any comments? Any questions? Brian? Adam? Karen? Any comments? Any questions? Did they hear yes or no, Karen? No? Okay. Okay, thank you, guys.